You've learned how to analyze the strength of an acid quantitatively by looking at pKa's of a certain group or a certain molecule. Now we're going to look at the strength of an acid qualitatively by considering factors that affect the stability of the conjugate base. So looking at this molecule here, we're going to compare two protons in an attempt to find the most acidic proton on this molecule. We'll be looking at this proton right here, this hydrogen, and this one here. So when we want to analyze conjugate base stability, the first thing we want to do is abstract the proton, just swipe it off. So we'll go ahead and redraw parts of this molecule down below to look at the conjugate base. So we draw this, nitrogen here, to the methyl group, and add the two lone pairs and the negative charge. That goes down here, and as for over here, I have this part, and then the oxygen holding the negative charge. And as you can see, I didn't draw out the rest of the molecule just because you want to look at these separate parts. One of the first things we'll want to compare is the type of atom that the negative charge is on, which you'd expect that more electronegative atoms hold negative charges better than less electronegative atoms. So let's make a comparison here. We notice that, okay, we have nitrogen over here, nitrogen on the left, and then oxygen on the right. Well, since oxygen is more over to the right on the periodic table compared to nitrogen, then it's more electronegative, and thus it handles the charge better. So in terms of the atom stabilizing the negative charge, this molecule wins, and I'll write an A here to represent atom. Another thing we can look at is the resonance that's in a molecule, and you've learned that. Well, we should notice here that they're both molecules express resonance. On the left, we can have the negative charge, or the lone pair, move here and push electrons from the pi bond up onto the oxygen. And if I redraw that below, then I have this molecule, just the lone pair right there. Same thing on the right. With this molecule, we have resonance. And I'll draw a lone pair here to move. But as you can see, we have more resonance structures, because once I draw this out, I have the double bond here. I know that I can move these around again and push electrons up onto the oxygen on the bottom, giving us another resonance structure, which just for time's sake, I won't draw out. So the molecule on the right expresses more resonance, which means it stabilizes its negative charge over a larger space. So we'd expect this atom to win over on this quality, going from atom, including atom and resonance. Of course, there are other factors, including induction and orbitals, but as you can see in the original molecule, we're not really seeing too many examples of induction. Yes, the nitrogen could have an effect on the sulfur, but it's so far away that that effect is going to be insignificant. We're not going to really even consider it. Same thing that goes for the sulfur on the other side of the molecule. And as for orbital, we're working with the same orbitals here, so that's not going to help us out. Considering the factors that we've looked at, in this case, the stability that a certain atom grants a negative charge, and the amount of resonance we see in a molecule, this would be the more stable conjugate base, and thus, this proton right here would be the most acidic proton. Sometimes, however, it can be a little more difficult to determine which acid is stronger qualitatively, because they'll share a lot of the same factors. And it's almost like an algebra problem, because if one side has the same factors as the other side, they cancel out. It doesn't really help us at all. So let's look at the following example. As with all problems you do in organic chemistry, you should be asking yourself, what are we working with? Who are the key players? Now, we know we're considering acids and bases here, because that's the chapter we're looking at. And looking at acids here, we consider that, okay, if I'm wanting to look at the stability, first step, deprotonate to get the conjugate base. So if we redraw these molecules out here, we'd have the negative charge on the oxygen, draw out the halogen down here. Same thing for the molecule on the right. The idea being that, once again, looking at the conjugate base gives us an idea of the stability and how willing a molecule is going to be to give up its proton. So let's start looking at some of our factors. Usually we start by looking at the atom that houses the negative charge. Well, here, if I write A to represent the stability of the atom, or the stability that the atom gives a negative charge, they're both on oxygen, and that that doesn't really help us. So they're going to be equal. So we're not going to gain anything from that. Now moving on to resonance. If I'll draw an R here. Well, they both exhibit resonance through these structures, and also the atoms that are involved in the resonance are the same because we have two oxygens and a carbon that's acting as the middleman, you might say. So resonance here is, once again, the same. Now we get into a few of the weaker effects. In this case, induction. Well, we see that, okay, we have an electronegative atom here on the left, and we have same thing here on the right. Well, we have two electronegative atoms, but they're different. Now, when it comes to induction, the two main factors that should come into your mind are distance away from the negative charge and how electronegative a certain atom is. So here, well, they're the same distance, so we'll want to look at which atom is more electronegative. And if we consider the periodic table, we know that in terms of the halogen column, chlorine is above bromine, which means it's going to be more electronegative, because if you remember electronegativity trends on the periodic table, as you go to the right, electronegativity increases, and as you go up, electronegativity increases. So here, we know that the molecule on the left is actually going to win out because the chlorine's electronegativity pulls electrodensity towards it more stronger, helping stabilize the negative charge. Of course, we could go ahead and consider the orbitals that these are located in, but for the atom, in terms of the negative charge, they're both housed in sp3 orbitals. So that would be the same. And of course, usually when it comes to orbital, you usually don't get down that far.